Hello, welcome back to Module 4, Working with EEG Data. In this lesson, we're going to cover EEG artifacts and preprocessing, Part 2. And as we already know, artifacts and EEG signals are a result of extraneous movements such as blinking or breathing, and preprocessing steps such as applying filters allows for some removal of artifacts. And some key questions that we're going to address in this lesson are: how can we minimize artifacts? How is preprocessing different in research headsets and consumer headsets? And what are some methods for artifact correction? In EEG data, each electrode's voltage is recorded relative to the other electrodes. So the reference can be one or a combination of electrodes in which the voltage would be relative to. In other words, the neural activity at the reference electrode will also be reflected in all the other electrodes, which could contaminate your signal. Therefore, your choice of reference can make a critical impact on your data. So when choosing a reference, it is important that the electrodes that you're selecting as a reference would have as little influence on the locations of your signal of interest as possible. So this means that either the references are located far away from the signal of interest or an average of several electrodes is used. So the average mastoids, which is the bone like behind the ear or earlobes, are typical reference electrodes. So these are generally good choices because the reference electrodes are like close to the other electrodes but record less brain activity. These are not necessarily perfect references because they are close enough to the brain to measure neural activity from lateral temporal areas, for example. And for a large number of electrodes, or if electrodes are placed on the neck and face, an average reference is often recommended. Referencing to one lateralized side is not recommended because this will introduce a lateralization bias in the data. So the reference electrode should not be close to an electrode where you expect your main effects. And the average of the two earlobes is also commonly used for similar reasons as the mastoids. And another common choice of reference is the average of all electrodes, also known as the common average reference, which reduces the impact that any single malfunctioning electrode will have on the results. Using this only makes sense with systems that have enough channels so that the overall activity averages to 0. And it's not recommended if you have less than 32 channels. Lastly, CZ, or the central electrode, is frequently chosen when looking at activity that is distant from that location. So CZ electrode would be a poor choice of reference if your analysis involves response errors which elicit maximal activity around the CZ electrode. And so that's all for referencing. And so again, artifacts are signals that are picked up by the EEG system but do not actually come from the brain. So EEG artifacts can be classified as either environmental or biological. Environmental artifacts originate from outside world interference. Examples include power lines, electrodes losing contact, or people's movements during the experiment. The easiest way to reduce the effect of those artifacts is by adjusting the environment. So for example, shielding the room or properly securing the electrodes. Power line interference can be removed by applying the notch filter at around 50 to 60 Hz as described earlier, and sometimes this filter already comes pre-built in some headsets. The influence of environmental artifacts can also be reduced by using active electrodes, which are electrodes that have an additional low noise amplifier inside of it. And then there are biological artifacts that originate from sources in the body. The common ones, as stated earlier, are blinks, eye movements, head movements, heartbeats, and muscular noise. You can detect those artifacts if you have access to other biometric data like the electrooculogram or eye tracking data for eye movement artifacts, accelerometer data for head movement artifacts, and electrocardiogram data for heartbeat artifacts. Sometimes the neural signals that are not relevant to the phenomenon you're investigating can also be considered as source of artifacts. For instance, participants who are tired will often show large alpha wave spikes, which you might want to remove if you're not interested in looking at that effect. So there's some differences in pre-processing between high-density research EEG versus low-density or consumer EEG. And high-density EEG systems are great for standardized research, whereas consumer EEGs can be used for like entertainment and self-help applications because they're more convenient and faster to set up. However, the consumer EEG's data quality can be negatively affected by artifacts due to using only dry electrodes. Overall, the main differences in pre-processing are in channel removal due to smaller amount of channels in consumer EEG, using event markers due to Bluetooth lag, data quality due to non-standard electrodes, and referencing. And with high-density research EEG caps, the occasional bad channel is simply deleted because there are enough other channels to compensate, so there's no significant impact on the data analysis being done. And in low-density EEG systems, however, the amount of channels is very limited, so rejection of noisy channels is not feasible. Therefore, it is important that whoever is setting up the hardware has appropriate training to reduce the noise. Next difference is using event markers. So event markers are a time measurement of when an event is expected to occur in order to simplify like ERP analysis. This is extremely common with high-density EEGs since they are already connected to a computer through cables. However, with low-density EEG systems, they are connected through Bluetooth, which has a lag of tens of milliseconds that varies in magnitude of tens of milliseconds. So the analysis cannot simply depend on event markers to indicate what sections of data to analyze as an event-related potential or ERP. Alternatively, some pre-processing protocols may identify the slope of change in a signal and identify that it is likely an ERP. Still, protocols without event markers are not really well established. And then next is data quality. High-density EEG systems are often employed with wet electrodes to provide better signal quality than dry electrodes. In low-density EEGs, which already uses dry electrodes, the issue of signal quality is further complicated by the limited amount of channels. Therefore, a bad channel cannot simply be rejected. However, sufficient quality can be easily obtained if users follow the guides for using these headsets more closely and gaining experience with this type of EEG system. The last difference that I'll be talking about is referencing and the ERP shape. With high-density EEG systems, many channels are available, so there are multiple popular options for referencing, such as the mastoid channels. But with low-density EEG, the hardware limits referencing options, so a common compromise is referencing to the FPZ channel. These hardware limitations can lead to the shape of well-studied ERPs to be different. So this does not necessarily alter the quantification of an ERP detected, so the analysis can still be successful. This occurs because the referencing isn't done with channels that are farther away, so the signal characteristics that stand out would be different and can lead to non-standard ERP shapes. The purpose of artifact correction is to remove neural signals that aren't useful for our analysis, but these techniques often intersect with the techniques used to pick apart different contribution to a measured signal, also known as source decomposition, and then estimate its localization in the brain through source localization. If two independent signals are statistically independent, even if they are added together, one can separate contributions that are not predictive of each other. and this is called source separation. And this would be done with independent components analysis, or principal components analysis, signal space projection, or other methods. And once the signals are separated, they can be localized by fitting them to fixed oscillating dipoles, and this process is called source localization, and it is often done with a dipole fit. So dipole fitting consists of modeling the brain's behavior as oscillating dipoles in specific positions. It's based on the concept that brain waves result from groups of parallel neurons firing synchronously, which can be modeled as a voltage potential dipole oscillating in a certain position. And the mathematical process of directly fitting oscillating dipole sources onto an EEG signal is not very trustworthy or resilient to noise, especially for deep brain signals. Therefore, a much more powerful approach is to apply dipole fitting onto individual signals that have been picked apart by an artifact correction algorithm such as ICA, which we'll discuss next. So ICA is a technique that separates and localizes independent signals that have been added together. So this can be sort of easily understood with an analogy. Imagine you're in a party and you're searching for your friend that you hear on the background. You attempt to isolate his or her voice from the other from the noise of other conversations, and this is what ICA essentially is about. For source separation, ICA is generally considered the best since it does not assume orthogonal or Gaussian behavior of the individual signals, which are unreasonable assumptions that other techniques depend on. And in any case, ICA still assumes that signals are static and that separate signals are statistically independent, which may not be appropriate for some neural signals. So for artifact correction, ICA is used to separate components in order to identify artifacts from eye movements or heartbeats. These have a characteristic shapes and can often be identified automatically. Applied to EEG and EMG, ICA is much more effective than its simpler counterpart, which is PCA, or Principal Components Analysis, which assumes that all signals are orthogonal and creates a succession of orthogonal base vectors where each vector will account for as much variance as possible. As a result, when using PCA, the first vector is significantly larger in magnitude than all the subsequent vectors, and when the signal-to-noise ratio is low, important information in these subsequent vectors can get lost. And there are other types of source separation techniques aside from PCA and ICA, such as SSP, which stands for signal space projection, that I won't be going over in too much detail, but basically SSP is similar to PCA in that it separates signal from noise based on orthogonality, and it makes the assumption that signals and noise are generated in fixed and different positions and orientations. So their contributions are linearly independent and show stable field patterns, even though they vary in magnitude over time. And generally, SSP produces less noise and less signal, whereas ICA carried noise forward but identified signals without reducing them. And so here's our summary. Because voltage values from each electrode are relative to one another, it is important to choose an appropriate reference point. The reference point, as well as the choice of environment, can help decrease the number of artifacts in the signal, and signal decomposition methods are used for artifact correction and include source decomposition, source localization, and source separation. And in the next lesson, we're going to cover Fourier transform. So I'll see you then.